Hello, students. Welcome to today's lecture. Today, we're going to study the drag forces. Okay. So, basically, when there's a flow against some solid particles or some bodies, so what kind of forces or what kind of drag is applied by the fluid on the bodies or particles? So, this chapter basically deals with the flow of particles through a fluid. Okay, so what happens if suppose basically we are studying unit operation, right? So what happens is we are going to handle solids, right? So this handling may result or may include like handling solids through a fluid. Let's say I want to separate particles like in airbag filter. Okay, so what happens? The dust particles will pass through air, right? So if the dust particles is passing through air, so it will experience some kind of force, drag force. It is called drag force by the fluid. Okay, so in unit operation, we are going to handle solids such that they are flowing through a liquid medium or through air, so they will experience some kind of forces, generally called drag forces. Okay, so that's why the study of drag forces is becomes very important, because then only you can predict how will the particles behave in the fluid. Okay, so this the flow of particles will be governed by Newton's third law. You already know what is Newton's third law. Okay, in Newton's third law said to every action there is an opposite and equal reaction. So if you are applying force to a wall, so the wall will give you a force of the same magnitude but in opposite direction. Okay, so only the thing is the force is acting on two different objects. One is acting on this object and another is acting on the wall. Okay, so from this, if the particle is flowing through a liquid, then what happens? So it is exerting some kind of force to the liquid, right? So by Newton's third law, the fluid will exert some kind of force in the opposite direction of that this particle, right? So this comes into play while studying the movement of solid particles through a fluid. Okay, so now we're going to study that only. Okay. So I will share you the PDFs with you. Okay, suppose, so we'll take a simple case. Suppose there is a object. Okay, let's consider spherical object. It is stationary. Yeah, it is at rest, and suppose fluid is flowing in this direction. Let's say air is flowing or liquid is flowing in this direction. The particle is stationary. Okay, it is not moving. So definitely what will happen? This fluid will try to take away this particle, right, along with it. So this is called drag. Okay, so fluid will apply some drag on this solid particle. Also, suppose the fluid is stationary. We have stationary fluid, and particle is moving, wants to move through the fluid. Then again, the particle is exerting some force. So the fluid will exert opposite force to the particle. Here, in this, the drag force will be in this direction, but here the drag force will be in direction. It's relative, right? So the object in this case is stationary. Okay. If the fluid is wants to move in this direction, that means the object wants to move in this direction, right? If you see relatively, okay. So if you take the stationary reference frame, like say this is origin. So what is it? The particle is stationary, the fluid is moving, right? Okay, so the fluid will exert drag force on the particle. Okay. But if you take the reference frame as the fluid, then you can consider that the particle is moving in this direction, right? It's just relative, so it doesn't matter. Anyway, if there is a force on the fluid, then it will also exert some kind of drag that is opposite and equal direction. Okay, so this was the simple case, which is spherical. Let's consider the general form. Okay, suppose we have a object like this. Okay, it is not spherical, it's some other form. Okay, so let's say fluid is moving in this direction with velocity v0. Okay, so it is given in here as well. Now, what is if you consider small area this here, obviously you have to calculate the whole drag force on this solid by integrating whole area. So before integrating, we'll just consider a small area dA, this sketch part. Let's say it is the area dA. So what is the normal to the surface? This direction, right? So if you want to find the normal to any surface, you have to consider 90 degree to that surface. So this is curved surface, so 90 degree will be here. If you draw a tangent and you draw a perpendicular on this tangent, this is your normal direction, right? Okay, so the force will have two components. One is called form drag and wall drag. Okay. So what is form drag? Form drag is like it acts in the normal direction. Suppose you have this rectangular plate and fluid is flowing in this direction. Though the form drag, this is completely form drag, right? It is acting in the normal direction. So it is nothing but fluid pressure, P. Okay. What if this plate is at an angle, right? And fluid is flowing in this direction. Then it will also experience shear stress. Okay. So shear stress you already know, I told you earlier. So shear stress is like you're applying force in this direction, but area normal is in this direction. Right? It is kind of shear action. So if this plate is in angle, so it will experience some shear force. That is called wall drag. Okay. Suppose if the plate is completely horizontal and fluid is flowing over this, there will be no pressure drag or there will be no form drag because there is no force directly to the normal direction to the area. This is the normal direction to the area and there is no force in this direction. Okay, so there will be no form drag in this case. Okay, but there will be only shear stress because it is parallel, right, to perpendicular to the normal direction but parallel to the surface. Then only there will be a shear stress. But if it is at an angle, right, then it will have both the pressure plus shear. Okay, so that's why we are taking a arbitrary surface at an angle. Okay, so that we can calculate the both the forces acting on that solid particle due to fluid. Okay, so we have two components. So we'll have pressure force and we have shear stress. Okay, and again we have two components for both the parts. Okay, so if you consider this sketch, okay, so fluid is flowing in this direction. Okay, you have considered this surface, small area dA. Okay, this area is dA. Anyway, you have to integrate over the whole surface to find the total drag. Okay, so what is the normal direction? This direction. So pressure will act in normal directions only. So you have pressure this. So what is the force? Force by A is pressure, right? So force is nothing but P into A, right? Due to pressure. So we have considered dA. So it will be PdA. So in this direction, let me erase this. So in this direction, we have pressure force, right? So PdA. Because pressure always acts in the normal direction. What about shear stress? Shear stress always act parallel to the surface and perpendicular to the normal direction, right? So this is the shear stress direction. Again, shear stress is defined as force per unit area, right? So it has same units as the pressure. So to calculate the shear force, you have to multiply it area. So again, it will be this force due to the shear will be tau dA. Okay, fine. Now you have to calculate these components in the direction of the fluid flow. Fluid is flowing in this direction, right? So you have to calculate this form pressure, that is form drag. It is called form drag if it is from the pressure. You have to calculate the component of this form drag or pressure in this direction of the fluid flow. So if you take this angle alpha, then the component of the pressure in this direction will be, already this is PdA, right? So PdA cos alpha. So this is form drag only because of the pressure. So PdA cos alpha is the form drag in this direction. Okay. Again, you have to calculate the shear force in the direction of the fluid flow, right? So you have to calculate the component of shear stress in this direction. So what is the angle? This is nothing. So if you consider this, what is this? These two are 90 degrees. So this is 90 minus alpha, right? And what is this? This is going to be, this is 90 degrees. So this is going to be alpha. Then what is this? This is 90 minus alpha, right? So the component of this shear stress in this direction will be wall tau W. This is shear at wall dA into cos 90 minus alpha, right? So now cos 90 is nothing but sine alpha. So tau W dA sine alpha, right? So this is your wall drag. So the drag because of the shear stress is called wall drag. Okay, and the drag force because of the pressure only, it is called form drag. Okay, wall drag is because of shear and form drag is because of pressure. Fine. So what is the total drag then? So the total drag will be equal to the sum of these two, right? So the total drag will be PdA cos alpha plus tau W dA sine alpha. This is the total drag on dA area, right? So if you want to find the total drag on the whole surface, then you have to integrate this. So you have to integrate this. Okay. Now you know the two components of the total drag force, that is, one is form drag. This arises only because of the pressure force, and wall drag, this arises because of the shear force, and sum of these two will give you the total drag. Okay, fine. So so now you can remember, right? What are the two forms of drag? It is, one is form drag and one is wall drag. Okay, and you have also calculated the formula. Okay. What we discussed earlier was, that is the drag force. Okay, so you can also express drag force in terms of drag coefficient. Drag coefficient is nothing but dimensionless. Okay, so what is drag coefficient? So it is defined as CD FD by AP rho U square by 2G. Okay, you ignore the GC part. This is just conversion factor. Okay. So this is the drag coefficient. This is dimensionless, no units. Okay. No units. So it is a drag force divided by the area. Okay. What is AP? It is projected area. I will tell you in a while. So this is rho U square by 2G. Okay. Rho is density of the fluid. U naught is the velocity of the fluid, and G is the acceleration due to gravity. Okay. This is called velocity head. Okay. If you have studied fluid mechanics, you will come to know that this is velocity head. Okay. It is projected area. So this is how drag coefficient is defined. Okay. So if you have studied the fluid mechanics, there also friction factor is there. So friction factor F was defined as shear stress divided by rho U square by 2G. So in a similar manner, this drag coefficient is defined. Okay. So this is friction factor. It is defined in fluid mechanics when the fluid is flowing through a pipe. Okay. So this is the drag coefficient. Okay. So FD is the drag force. If you know the drag coefficient, you can calculate the drag force, right? And rest will be given. So what is AP? Okay. So let me clear you on the projected area. So what is projected area? Suppose you have a ball, right? If you put a torch here, then what will be the shadow? This is ball, right? Ball, 3D. What will be shadow on the wall? It will be circle, right? This is a shadow. If you put a torch on a ball, that is sphere, and you'll get a shadow of circle, right? So this is called projected area. So suppose fluid is flowing like this, and you have a sphere here. The fluid will see this sphere as a circle, right? So that is called projected area. While calculating the drag coefficient, you have to calculate first the projected area. Okay. So if we have a sphere of diameter dp, this is sphere, what will be the projected area? So it will be the circle of diameter dp, right? Circle. So what is the area of this circle? Pi dp square by 4. Okay. Okay, one more example for projected area. Suppose this is the fluid flow, and there is a one cylinder lying like this. The axis of the cylinder which passes through the center is along the direction of flow. Then what is the projected area? This, right? The fluid will see as this circle. So if the diameter of the cylinder is dp, then again it is same, I d square by 4, right? This is the projected area. What if the cylinder sits like this, in this way, and fluid is flowing in this direction? So what will be the projected area? It will be seen to the fluid as a rectangle, right? So what is the length of the cylinder? Let's say it is L. What is the diameter? This is dp. So what is this area, projected area for vertical cylinder? L into dp. Okay, this is how the projected area is calculated. Okay. Now the drag coefficient. So how to calculate this drag coefficient? So generally you don't have a general formula to calculate drag coefficient, but you can calculate drag coefficient from experiments. Okay. So if I have a sphere, I have a cylinder, so drag coefficients will be different, right? They will be not equal. Okay, if I have a particle of irregular shape, then the drag coefficient you cannot predict by using formulas. Okay, you have to do the experiments. Okay, so generally the drag coefficient, it depends upon the Reynolds number. Okay, so we'll see in a bit. So for any shape, right, CD is a function of the Reynolds number. The shape can be a sphere, cube, or cylinder, okay, or any irregular shape. So from experiments, it can be found that it is a function of Reynolds number. So if you have a high velocity fluid, then obviously more energy, right? So by Newton's third law, the opposing energy will also be high. So for high velocities, you'll have higher drag force. Okay. For lower velocities, you'll have lower drag force. So it is kind of directly proportional. And what is Reynolds number? How you define Reynolds number? Rho V d by mu, right? What is d? D is the particle diameter. What is velocity? Velocity of the fluid. Okay, and what is mu? Mu is the viscosity of the fluid. Okay, so here it is given as GdP. Okay, so rho v is nothing but what? It is flux, right? So kg per meter cube into meter per second. Meter, this becomes square. So kg, so it is mass flux, right? Rho v is nothing but mass flux. And G is nothing but mass flux only. So rho b, instead of writing rho b, it is given G. That is mass flux. So here it is also given. So the dP is called characteristic length. Okay, for sphere it is dP. For short cylinders, it is also dP, right? Because short cylinder dP is equal to length. Okay, generally what is characteristic length? So see, I can express any particular length as something, and you can express other lengths in terms of that length. Okay, suppose I have a long cylinder. So what is the diameter? Let's say dp. So I can always express this length as a some, let's say 2 times of dp. Okay, this length of the cylinder. So this is the primary. If I using primary dimension, this is your characteristic length. Okay. Okay, fine. So now how the drag coefficient varies. So how the drag coefficient varies, with the Reynolds number. So I told you this drag coefficient is a function of Reynolds number, and the function is different for different shapes. Okay, for cylinder it will be different, for spherical shape it will be different, and for other shape it will be different. Okay, so let's consider this Stokes law. Okay, so this is, let's say I have a sphere. The drag force Fd for a spherical particle, right, is given by Stokes law, that is 3 pi mu velocity u naught into the particle diameter. Okay, as you can see from, ignore this gc part. This is a, you can say gc is equal to for SI units. You have to take gc is equal to some value for other units, right? So British units. So if you're doing in SI units, you can safely assume gc is equal to 1. So don't bother it. Okay, so this is the drag force given by Stokes law for a spherical particle. Only the thing is, this formula is applicable only if the Reynolds number is less than or equal to 1. So if the Reynolds number is less than or equal to 1, then you can apply this, Stokes law for a spherical particle. Okay, and so from this, once this Fd is given, you can calculate the Cd, right? How? For this Reynolds number and for spherical particle, you can calculate the drag coefficient. What is the formula? Fd by AP, and here you have rho u naught square by 2g, right? So what is Fd? This is given by this. If you put here, and what is the AP? The projected area of a spherical particle is pi dp square by 4. So if you calculate this, so I will show you. Actually, d is equal to Fd was 3 pi mu u naught dp, right? And what is the projected area? It is pi dp square by 4. So 4 goes up. Okay, and you have the velocity head rho u naught square by 2g. So 2g goes up. Sorry, this was gc in earlier case. So we have velocity at rho u naught square by 2 only. So this is nothing but gc. So that is the value is 1. So okay. So now you just cancel the terms. Pi cancels out. dp, this becomes dp. Okay. So dp rho, this mu naught, this becomes mu single velocity. So if you write down, so what are left? 4 into 3, 12. 12 into 2, 24. Okay, then what you have? Mu by rho dp u naught. You can rearrange this, right? So 24 by rho u naught dp by mu. This is nothing but Reynolds number. So 24 by Reynolds number, right? And RE is nothing but Reynolds number. You can write like this, or you can simply write Reynolds number. Okay, so if the Reynolds number is less than 1, you can calculate the drag coefficient by directly 24 by Reynolds number. Okay, and the drag force is given by the Stokes law. Okay, so you remember this. And you might ask, what happens if the Reynolds number is greater than 1? Okay, so it is called, so we will be having two flow regimes. So one is Stokes regime or Stokes flow, another is non-Stokes regime or non-Stokes flow. Okay, this Stokes flow is for RE less than equal to 1, non-Stokes flow if RE is greater than 1. This. Okay, we'll study this, both the cases. Okay. Now, if you calculate the drag coefficient for, different particles, say versus the Reynolds number, then you'll get something curved like this. So we, on the x-axis, we have the Reynolds number. Okay. On the y-axis, we have the drag coefficient. It is defined by FD by AP and rho units squared by 2. GC you can ignore, take 1. Okay, so for spheres, the dark line, this one. On discs, this one, and the cylinders, this one. The drag coefficient varies something like this. Okay, so for very high Reynolds number, the drag coefficient is decreasing, right? And for very low Reynolds number, I told you this 1, right? So from 1 to this, you can say up to this. Up to this, it is Stokes flow. Okay, and above this, it is non-Stokes flow. So the drag force FD is equal to that given by Stokes law. It is applicable in this region, and here it is not applicable. Okay. Okay. In the next class, we will derive the terminal velocities of the particles moving through a fluid. Okay. Thank you.